Just wide open physics questions.
Yeah. So we're gonna kind of maximize this by allowing you guys to ask questions, and then you can go back and listen to the previous recording. And I guess if we record them both, then the other class can listen to our questions as well, and that's double the fun or something like that.
The racetrack in a circle quiz problem. How do we do that?
The racetrack in a circle quiz problem.
Yeah, it was you're in a race car traveling in a circle, and you need to find the acceleration.
Aha, good. So what I reviewed with the other class is that when you have a case of constant circular motion, the word constant here refers to what? What is constant in constant circular motion?
No,
What?
because the speed.
The speed, exactly. We have constant speed. And when we have constant speed, we showed that the acceleration has a value of v squared over r. Philip, would you mind closing the door, please? Thanks. We also very carefully showed the direction of the velocity and the acceleration. Which way does the velocity point at all times? Tangent to the circle. So my velocity vector is going to point like this. By the way, that's true for non-circular paths as well. Velocity is always pointing tangent to the path, whatever that may be. And if we are experiencing constant circular motion, then the acceleration is going to be centripetal. It's going to be straight inwards. Now, in this particular case, is our car experiencing constant circular motion? So we think about the car. How does it start? It starts at rest, right? And then it, here's our word, accelerates up to some kind of top speed. Is that constant circular motion?
No.
No, it doesn't have constant speed. That's exactly right. So how does that change things? Because we have non-constant circular motion. If we have non-constant circular motion, then we are going to add to our centripetal acceleration an additional component of acceleration that is tangent to the circle that changes the speed of the object. So that we are now going to have, in a different scenario, a velocity like so. And we're going to have a centripetal acceleration that points inwards towards the center of the circle that still has a value of v squared over r. We're going to add to that a tangential component that is going to change the speed. If the car is speeding up, that tangential component will be in the direction of the velocity. And if the car is slowing down, then the tangential component would be backwards against the velocity. But in this particular case, the race car is speeding up. When we take these two components and add them together, then we get an acceleration vector that points like this. That's AC plus AT, just like so. Okay? So that's the qualitative answer to your question. Now let's look at that specifically quantitatively. How quickly does our car want to accelerate? How about from 0 to 60, 0 to 30 meters per second in 6 seconds? Okay? So we're going to... And let us ask about the acceleration of the car at the start of this time, t equals 0, and the end, t equals 6. Notice at the end, the car isn't stopped. The car's going really fast. So we're just turning on the camera for 6 seconds and watching the car. And we want to know its acceleration at the start and at the stop. Okay? So we're going to think of the acceleration as having two components, AC and AT. And the AC is going to have the value of v squared over r at every single time. And the AT is going to be the acceleration that changes the speed, and that's going to be the change in speed over the change in time. And the change in speed over change in time is easy to compute. It's 30 minus 0 meters per second over 6 seconds, or 5 meters per second squared. The centripetal acceleration is the thing that is going to change. The tangential acceleration is not going to change for the entire trip. The centripetal acceleration will change because the car is getting faster, and therefore it must accelerate more towards the center of the circle to keep from sliding off. So at the beginning, at t equals 0, what is the speed of the car? 0, and therefore the centripetal acceleration is going to be 0 squared over r. We didn't specify a radius for our circle. Let's just call it r. And at t equals 6, what is the speed of the car?
36 per hour.
What is the speed of the car at
Oh, at
30 meters per second? That's right. And so AC would be 30 meters per second squared divided by r, or 900 over r. So now, what is the total acceleration? Well, if I express it in terms of components, the total acceleration is going to be centripetal and tangential. Usually, actually, we put the tangential first, but I would take either one. This is the total acceleration. And it necessarily has two components because centripetal and tangential acceleration are always perpendicular to each other. Does that answer your question?
Yes, it does.
Good. Other questions? Great. I'm going to ask you guys a question.
All right.
Take a look in your book on page 100. And take a look at problem number 31. And what we have here, they don't give us any values. They do tell us that the MA is resting on a smooth surface. What is that code for?
No friction.
No friction, that's right. Smooth surface is specifically code for mu equals 0.
Which is amazing.
Yes.
Really smooth.
On the bottom.
Oh, I see. Yep. Wayne was helping me out. I think he didn't know where to find it. And now they ask us this question. They ask us, draw a free body diagram for each block and find the acceleration. Go. Free body diagram for MA. Who's got it? Heaven O.
Quick question, this is going to be an end line.
Yes.
Oh, free body diagram?
Yep.
I drove MG
down,
Okay.
and then
How did you label that? We want to be really picky here. How are we going to label this?
um, MA.
Yes, that's right. The mass that is given to you, which is MA, that's the mass you're going to use. All right. What else?
Then FN.
Which way?
Up.
Good.
And right side, I wrote tension.
Good.
And then, yeah, that's the first one.
That's the first one. Good.
Second one is downside, I MBG.
Uh-huh.
And then tension. Up.
Good. You labeled this tension and that tension as the same tension. Why did you do that?
Same rope, same tension.
Same rope, same tension. Very good. Okay. Good. Everybody check your free body diagrams. They should be exactly this.
Cells 5.
No.
Okay. Now we need to do some acceleration finding. Alex, you got it?
I said that some forces and then so I said acceleration is no force
Okay. Tell us why that's as far as you got.
because of the lack of numbers.
Okay.
I couldn't find it.
Never let the lack of numbers be an obstacle, because you actually don't lack numbers. You've got a number right here, it's T. And you have a number right here, it's MDG. You've got another number right here, it's MAG. Those are numbers, you just don't know the values. I do have one objection to what you wrote. You have sum of forces equals MA, but we have no M present on our diagram. Which M did you mean?
It just said find acceleration, it didn't say which.
Ah,
It said which block.
didn't say which block.
Aren't they
That's a really interesting question. What?
Aren't they connected?
They are
They're one thing, so M is just M was.
That's a possibility. Does everybody hear that?
You just call it a system.
We can create, yes, we can call it a system, and we can do it as a system. I kind of like that.
You haven't failed us. Or we haven't failed you. Whichever way you want to look at it.
The system approach says, let's do the whole thing all together, and we're going to do sum of forces on the whole thing. If we're going to do the system approach, then we have to think of both of these guys as tied together, and the internal action-reaction pairs cancel out and have no effect. So if we consider it in that sense, then what are these forces acting on the system in the direction of the acceleration, which is over and down?
Tension as well as the MBG.
The MBG and the tensions cancel out because they're internal to the system, right?
And just then.
Just the MBG. And that has to equal now mass times acceleration. And what is the mass of the system?
M.
MA plus MB.
Mm-hmm.
MC.
And now we have a very easy solve, which is that acceleration is equal to MBG divided by MA plus MB, and we like it. Total force over total mass. Does the system approach make sense to everybody here? This is actually the favored way of doing things if you can possibly do it. Notice that all of the internal forces didn't matter. We looked only at external forces outside the system. The second approach would be to do a component approach. And here we're going to take each object, each component, and apply Newton's law separately to each component. And if we do that, it looks like this. The sum of forces on MA is equal to only the tension. I'm ignoring these forces, normal and MAG, because I know already that this object is not going to levitate up off the table. And so I know that the acceleration in the vertical direction is 0. I'm not particularly interested in that direction. I'm interested only in the horizontal direction. So I add up the forces in the horizontal direction, and I get just T. And that sum of forces must equal the mass of that component times the acceleration of that component. Good so far? Yes? No? Okay. And then I do the same thing for B. And the forces on B are going to be mvg minus the tension, and that is going to equal the mass of B times its acceleration also. Notice that I have two equations in two variables here. The acceleration is not known, and the tension is also not known. So I'm going to need to solve by substituting or by eliminating. It makes a whole lot of sense to do substituting because I already know what tension is. And so when I substitute in for the tension, then I get this equation, mb times g minus ma times a equals mb times a. Like so. And like so. And like so. And we get the exact same value of the acceleration we had to. Which one of these is preferred? Well, if you can see how to do it as a system, it makes a whole lot of sense to do it as a system. But if you can't, you can always break it into piece by piece by piece by piece. The cost is that you're going to get more variables.
And waste time.
And waste time.
Well, not waste.
No, literally. Waste time. Good? So, I think we have about 10 minutes here. I'd like to do one more.
Are we gonna get the different packets?
The packets are up on the line. They're ready to go. And I condensed everything into two. Number 18 on page 66, a good old projectile problem.
And usually it's over, but you never turned it.
A diver running 1.8 meters per second dives out horizontally from the edge of a vertical cliff.
And hold it up.
Dives out horizontally from the edge of a vertical cliff.
Belly flop.
Yeah, well, presumably that person will rotate as
I hope.
and 3.0 seconds later reaches the water below. So we're going to assume that it forms a path here. What's the name of the shape of the path? Parabola, which belongs to what family of functions that you know and love?
Quadratic.
Not exponential. Quadratics. There we go. And all that we know is that it takes the diver 3 seconds to hit the water. And the question now is, the questions are, how high is the cliff and how far from the base does the diver hit the water? I will give you 2 minutes to think about and do the.
It's like acceleration.
You have to use it. I know you have to use that.
So then, if the starting velocity is 0, and then times
I'm going to contradict you a little
3
bit.
seconds it takes to fall.
I'm going to contradict you a little bit. You don't know how to do it. You don't know how to do it. Knowing means I can do it.
I could probably figure it out.
Not quite, yes. Okay. That's probably a fairer statement. No idea to do it means you got it. You got it? Okay, so this is a classic example of what keyword did we use to describe this kind of problem? Projectile, that's right. This is a projectile problem. And the key things for the projectile problem were, first of all, to begin with an initial velocity in rectangular form. And this one is particularly convenient. What is the rectangular form for the initial velocity, Christian?
In rectangular form, it would be 1.0.
Point it. It's exactly so. 0 because there is no velocity component in the vertical direction. And now, having done this, I'm going to use equations of motion in the vertical and horizontal directions separately. In the x direction, do I want to use a delta x equation or a velocity equation? Delta x.
Yeah, as you're looking.
I'm looking for delta x. And so I say that delta x is equal to v0t plus 1/2 at squared. And I go to the initial velocity to read that initial velocity straight off of the vector. What is the acceleration in the x direction? 0 and not 9.8. Gravity does not pull sideways. So now to know the delta x, all I need is a t-value. You have a t-value, all right. So 1.8 times 3, which is 5.4 meters. And there it is. All right. Now we're going to repeat the whole thing in the y direction. Do I want a position, a displacement, or a velocity equation in the y direction? Displacement again, because I'm trying to find out how high the cliff is. And delta y is therefore equal to v0t plus 1/2 at squared. In the y direction, the initial velocity comes straight off the velocity vector, which is 0. The acceleration in the y direction, negative 9.81, which we are going to call 10. So that the delta y is equal to negative 5t squared. Oh, if I only had a time. I have a time, that's exactly right. And I can do this in my head. I get negative 45 meters. So the cliff is negative 45 meters high, right? No.
If your reference frame is from the top.
Wait, I don't. You change 0 should be negative. Like, it should be negative y0 equals 1/2 negative 10 times.
Y is 1, 0.
Yeah, that's right. Yeah. Negative y0, because that's delta y. The final y is 0. The initial y is y0. And so y0 is therefore equal to 45 meters, which is the height of the cliff. And there it is.
How are we gonna remember all this stuff?
How are you going to remember all this stuff? Great
I
question.
forgot all of this.
Go back and find it.
Great question. Everybody forgets projectile problems because they are involved, right? They require us to split out x's and y's and so on and so forth. I strongly encourage you, first of all, to watch the first video where I talk about these also. And second of all, to go back and practice projectile problems until they are comfortable for you. They're not hard, they're just long. You know what I'm saying? So there it is. I think the bell's going to ring. I hope the bell's going to ring. Have a good day.